Hello, Science Alliance. I'm Lara. This is Theatre of Science. I'm actually trained to teach physics to A-level. So I like this bit of my job because I'm streaming free live IGCSE lessons into the internet. And I don't want to escape, but it's not a million miles away from physics A-level, actually. So we get... oh, all right. Last lesson, I gave you a sheet of questions. I forgot to mention it. I totally forgot to mention it. So very quickly, here is the answer to last week's pressure question. A good little bit of revision for you. It's always a good idea to go back, isn't it? You're planning a journey to the bottom of a strange planet's ocean. You get me? You're on a different planet where maybe gravity is different. There's an atmosphere and there's an ocean. You want to go down to the bottom of the ocean. The pressure on you will depend on the pressure that you experience as you go down and down into that planet's ocean. What does the pressure on you depend on? It's more than one of these. The ocean's density. This is actually great, isn't it, to have had a week off and then have to do this again? Because you'd have probably been really confident last week and now you might not be so sure. The ocean's density, like how close together the particles are in that ocean, if you like, could be water, but it could not be. The ocean's mass, how deep you go, the planet's atmosphere, like the gas around the planet above the ocean, the volume of the ocean, the planet's acceleration due to gravity, little g, right? If you like, the amount of gravity that the planet has. Your weight, which of those do you reckon? It's like I said, it's more than one. You need to do some calculations because you're going deep down to the bottom of a strange planet's ocean. Don't try this at home, children. I think that's quite a good question, actually. If only I'd remembered to ask you it last week, but I think it still counts as a good question. Oh, you ought to remember the equation for pressure, didn't you? Pressure in a liquid. Do you remember? Remember? Was it something to do with mass or density? Okay, the answers are, because we need to crack on with this lesson. Here's the equation. Change in pressure as you go deeper and deeper down into a liquid. The change in pressure is equal to the density of the liquid times little g times the change in height. So the pressure on you depends on, it does depend on the density of the liquid, so it depends on the ocean's density. Does the ocean's mass depend? Is that changing anything? The answer is no, because it's just the amount of particles above you, right? How deep you go, definitely, because that's a change in height, how low you are in the water. The planet's atmosphere does, yeah, it does, because that's pushing down on the ocean, so that counts. And just one more out of those three, it's the planet's acceleration due to gravity, little g as well. The volume of the ocean, how much water there is in the ocean makes no difference. It's just the amount of water that is above you, and your weight makes no difference either. Okay, right, phew, right, we can move on. Hello everyone, welcome to this lesson, which is all about solids, liquids and gases and how substances change from one into the other. So very quickly, because I haven't really taught you this yet, but I just keep showing you this diagram and going, oh, of course, because this is true. If we're just going to say that particles are little balls, which we can for this lesson, then you can think of the particles in a solid as being kind of neatly lined up together. Like generally speaking, the particles in a solid are quite densely packed together and they're all bonded together. The particles in the liquids, careful because this can catch people out. They are touching each other. They're not all really spread out. They're touching each other and they are bonded together, but their bonds keep breaking and then reforming and breaking and reforming. I always say it's a bit like a ball pool. If you imagine the balls in a ball pool, like they're touching each other and they can move around each other. But there are chemical bonds between the particles in a liquid. They just keep breaking and reforming, so they're still touching. And gas particles, really spread out, completely free, not bonded together at all right? We have said before that everything in the whole universe is vibrating a little bit. Everything's always moving around a little bit. This is important for this lesson. So the particles in a solid, the particles in a gas are free to move around. They're moving around a lot. You can tell because of all these little cartoon lines that I've drawn here. But the particles in a solid, you've got to be really careful, and I'm going to try and use really precise language today. They are still vibrating. They're just, if you want the really posh physics word, they're oscillating. They're like moving to and fro around a fixed point. So you can do it with a fist. They're sort of doing that. They are moving, they're vibrating, but they're not they're not travelling around anywhere, unlike the particles in a liquid or a gas, which are sort of a bit freer to go on a journey. Is that all right? Anyway, I asked you, while you were hanging around waiting for me to start the lesson, if you could have a go at filling in the gaps on this little diagram. This is me teaching you these words, so don't worry if you couldn't do it, but I thought it'd be interesting to see how much you just got from everyday experience of living on planet Earth. You probably know that when a liquid turns into a solid, what's that word? Water's the easiest one to remember because humans talk about water a lot. When liquid water turns into solid water, you're probably comfortable with the word freezing. That is what's happened. When a solid turns into a liquid, when solid ice turns into liquid water, we say that it is melted, and that is the proper science word you would use in your exam. Gas turning into a liquid, we talk about condensation, don't we? If you have a shower, then the very warm water particles end up kind of freely moving around in the air, and when they hit the cold mirror, they condense and turn back into a liquid. I thought this was the one that you might have got wrong from everyday life. When a liquid turns into a gas. We say that it's boiling. Some people on Facebook were a bit tempted in the comments to say evaporation, but we will do that next lesson, so don't worry. What we're going to talk about today is how substances move from solids to liquids to gases and back again, and these are the 4 words that we're going to need. There is sublimation as well, which is fun, when something goes straight from a solid into a gas and misses out liquid altogether. If you like the theatre and you see a lot of special effects at the theatre, like sort of dry ice, then that's what's happening. But mainly we're going to talk about freezing and melting. If you're doing an activity with me, you need a bowl full of ice cubes. I've used quite a lot. You could just use 1 ice cube, that'd be fine. I've decided that because I'm a teacher and I've never done the activity with sugar before, I'm going to do the activity twice, but you can just do it once. So you just need some ice cubes in a bowl, and you need a piece of string, and I said to bring some salt or some sugar, but yeah, I'm going to use both, so you could be getting that set up while I'm chatting to you. Okay, let's start really basic. So water as a solid, once it gets to 0 degrees, it melts, okay, into a liquid. So we say that 0 degrees is the melting point of water. You've got solid water, which is at minus 20 degrees, minus 10 degrees, minus 5 degrees. Once it gets to 0 degrees, maybe I should have said it starts to melt. It starts to melt. So we say that 0 degrees is its melting point. This is not a coincidence. Humans made up the name 0 degrees because that is the temperature at which solids melt into liquids if they're made of water. So yeah, not a coincidence. And you probably know the boiling point of water as well. Again, not a coincidence. Humans made it a lovely, nice round number because this is how we worked out a temperature scale. We'll talk about temperature again, another lesson. Once water gets to what degrees? 100 degrees, then it boils. So we say that that's its boiling point. That's when it starts to boil. We don't really talk about a condensing point because lots of things can make a gas condense. Like if you've just got loads of water particles in the air, if it's very, very humid, then water particles just cannot fit into the air anymore. So they start to appear as water on things. Like if you've ever seen dew, maybe fresh dew on the grass in the morning, it might just be that there was too much water in the air and some of it had to come out. So it's not like at a precise temperature condensing happens. Generally speaking, freezing, you can talk about freezing as well. We're mainly going to talk about melting points and boiling points. Yeah, you can cool some liquids to below their freezing points and they don't become a solid. We say that they're super cooled. So that's another reason for not talking about freezing points, because it's not as clear cut. But you cannot heat a solid to past its melting point and it stay a solid. Okay, just in case you were going to get funny with me about, well, why isn't there a condensing point or a freezing point? And I find this stuff quite difficult to get into my brain. I never know whether to say up or down when talking about freezing or melting points. But yeah, everything has a freezing and a melting point. So if you brought like a metal spoon with you, well, it's got a lot of sugar on it. Metal, like you're in a room, maybe the room you're in is about 18 degrees. The metal in your room is a solid, right? You probably haven't experienced liquid metal because we don't generally have like household temperatures that melt metal. But obviously, if you could get metal hot enough, I say obviously, it's not wildly obvious, is it? Like wood doesn't melt, for example. But a metal like iron, for example, which is all made of one type of particle, if you get metal hot enough, then eventually it will melt. And if you heated it up even more, it would turn into a gas. The oxygen that you are breathing in right now is already a gas. So we know that 18 degrees is well past the, what point? 18 degrees room temperature. If the oxygen that you're breathing in is a gas, then we must already at 18 degrees be well above the boiling point of oxygen, right? And the melting point of oxygen. If you could make the oxygen in the air around you cold enough, eventually it would condense into a liquid. And if you got it even colder, don't do it, but it would eventually freeze into a solid. Okay, a little bit of something for you to do, and then we'll move on to our activity. This is an activity that actually does get done in the classroom. I had to do this as part of, I think it was A-level physics, maybe it was GCSE, I can't remember now. Let's imagine, some people say that physics is boring, right? Imagine you've got a cup with frozen ice in it. How am I going to show ice? I'll just write it. Imagine you've got a thermometer in that cup, which is full of ice. And imagine you've put that cup, this is one of the best science lessons, underneath a flame, okay? So we're putting heat energy into the ice. If you've seen my energy lessons, the ice is getting hotter and hotter and hotter and hotter. Heat energy being transferred from the flame to the ice, right? So the particles of ice, we talked about how they are bonded together fairly rigidly, but they're vibrating, and as they get hotter, they're vibrating more and more and more and more and more, until eventually they turn into a liquid, eventually they turn into a gas. Well, I don't want to do any spoilers, I don't want to tell you wrong. I want you to try and fill this graph in for me. If you've got the free printouts from my website, you've got this in front of you. If not, I've tried to make it very easy to sketch. Imagine that scenario, right? You've got a solid block of frozen water, ice if you will, and it's been heated up until it becomes a gas. Can you sketch a graph to show what you think would happen to the temperature of the water over time? I am very much hoping that you're all going to make a mistake here. To be honest, if you don't make this mistake, you probably don't need to be at this lesson. So time is going by. You're heating this ice up and up and up and up. You're looking at the thermometer. So like you would, and again, like when I did it, you would keep watching the thermometer. You'd have a stopwatch ticking, and maybe after like 10 seconds, you'd check the temperature and write it down on your chart, your graph. And then after another 10 seconds, well, you'd put it obviously in a table of results, and then you'd put it in a graph later. But let's say 10 seconds goes by. What's the temperature on the thermometer? 20 seconds goes by. Now what's the temperature on the thermometer? 30 seconds goes by. Now what's the temperature on the thermometer? What do you think the graph that you eventually draw looks like? If you have got the free printout from my website, I gave you a small version of this because I'm fully expecting and kind of hoping, because it'll help your memory, that you'll get this wrong. So, what I was hoping that you would do, I don't want to rush you. What I was hoping you'd do is you'd just draw a straight line. Is that what you've done? Just draw a straight line. Time goes by, ice gets hotter and hotter and hotter and hotter, so I was hoping that you would just draw a straight line so that I could show you this and you could be like, what? Laura, explain that. What's happening there? I've put, what's going on? What is going on? What? We haven't put the fire out. We've got our flame burning continuously underneath the block of ice. Time is going by. Energy is being transferred continuously from that flame to the what started as ice. We haven't turned the flame down or turned it up. What are these flat lines about? There are periods of time goes by, and that thermometer temperature stays the same. So where is the energy going? Where is the energy going if it's not going into heating up the water? It's not going into making the particles actually move around more. Where is it going? I need to draw more diagrams on the board. Do you remember I told you that solids are all bonded together? The particles of ice get hotter and hotter and hotter. Their temperature goes up and up and up and up and up. And they vibrate more and 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 more. Careful, they don't start to vibrate. Remember, everything's always vibrating. But they vibrate more and more and more and more. The more energy they get. Until eventually, they start to change into a liquid, which means that the bonds between them break. So there's a period of time just at the melting point where instead of the energy going into making the particles move more, the energy goes into breaking the bonds, which is why the temperature stays the same. It's good, isn't it? It's like witchcraft that you can actually do this and observe this happening. So, yeah, I'll get you to do this and then we'll do the ice activity. I don't want to tell you too much. Can you, if you didn't get this, which I'm hoping you didn't, can you please sketch this answer? And then can you put a wavy line under the bits of the graph where melting or boiling are happening and label them, melting or boiling? And can you draw crosses to show where melting and boiling is starting to happen and label those as well? And can you do the same as number 3, but for freezing and condensing? Thanks for liking this video, chums. Do subscribe as well and all that if you haven't subscribed. And there's a post on my Facebook page at the moment, if you're watching live, saying that you can comment on my Facebook page if you would like to, excuse me, and I will read it out at the end of the lesson, because you'll have noticed there's no comments on YouTube. If you've finished, you can be, I suppose you can be putting some string onto your ice cubes. I'm very nervous because this didn't work very well yesterday at all. I don't know if it's a string issue, a science teacher issue, I don't know what it was. But I'll just do exactly the same thing again. That'll be fine. So have you got clear in your head where the ice is, where it's melting, where the liquid is, where it's, careful, not evaporating, boiling, where it's boiling, and then where the gas is? Can we go through it? So the places where the melting or the boiling are happening, the melting and boiling, if something is melting or boiling, that means that the bonds between the particles are starting to break. So the energy is going into breaking the particles. I don't know why I'm doing this. The energy is going into breaking the particles instead of making them move around more. So those flat lines are the melting and the boiling happening. So this is ice here, handily done in blue. Where that stays still, time goes by and it doesn't get hotter, that's melting happening, the bonds breaking to form a liquid. So this green line here is when it's a liquid. And eventually the bonds start breaking between the particles in the liquid and they become completely free to leave the liquid and they boil off. And that's this flat line happening. That is boiling happening and then it's a gas up here. Do the same for condensing and freezing. Sorry, draw crosses to show where melting and boiling is starting to happen. That would be right at the start here. So if you want to label those, that is your melting point and your boiling point, because it's when the melting point and the boiling point is when they start to happen. You might think it should be, the melting point should be when all of the substance is melted, but it's not. It's at the beginning. It's just when it starts to melt and when it starts to boil. And freezing and condensing, like I say, you don't have a condensing point, but on this graph, we would say that condensing is starting to happen here. This is the gas, this red line, and this flat line here, if we were to work backwards, this would be where condensing was starting to happen. And this would be where freezing was starting to happen. So I've seen quite a lot of stuff on the internet, people being confused about how, like, the melting point and the freezing point, how can that be the same temperature? Like, how can 0 degrees be the melting point of ice and the freezing point of water? Like, how can something be freezing and melting at the same time? But it's because it's just starting to do that. So if you get water to 0 degrees, it will be starting to freeze. And if you get ice to 0 degrees, it will be starting to melt. Is that all right? Let's do this activity. So what we need to do is you need to get ice cubes and just put some wool so that it's touching the ice cubes. I'm really paranoid because this has always worked for me, but it did not work yesterday on YouTube. So get the string so that it's touching the ice. Like I say, I'm doing it twice because I've never done it with sugar. I'm going to do it with sugar as well. And then you get some, traditionally, salt. I've done it on the wrong side, haven't I? You can more or less see that. I'm going to get some salt and I'm going to sprinkle it on. In fact, I'll put it on the table and then maybe I can be a little bit more focused. Make sure it's going where the string is, okay? I'm going to really put it on the string. Oh, I hope this works. There we go. Right, and then leave it for a minute. And this one, I'm going to sprinkle some sugar on because I've read that sugar works as well. I don't think I've ever actually done it with sugar. Okay, now I'm stopping. And I'm worried that I've put too much on. Oh, I think you're really just talking a pinch. Anyway, the internet says we have to leave that for about a minute now. Oh, God, it's not going to work, is it, guys? It's not going to work. Let's move on. Let's try and learn some physics while we're waiting for it to potentially not work. Here's your instructions. Put a piece of string on some ice, sprinkle on some salt and wait 1 minute. What happens? It sounds like a silly question. Why is the ice frozen? Don't say because it's been in the freezer. Why is the ice frozen? What does the salt do to the bonds between the water particles? What does this do to the freezing point of the water and the melting point? I'm going to tell you because there's no reason why you would know. Shall we see if the activity has worked? Shall we? Is it too soon? I don't know. I'm going to try. I'm going to lift it. Are you ready? Oh, it is sticky, but I don't know. Can you see that the string is kind of... Oh, yes, chums. Well done for coming to the YouTube version of this lesson. Whoa, so the ice is actually stuck to the bowl and the string is stuck to the ice, so I'm lifting up the entire bowl. Oh, the YouTube version of this lesson is always so much better than the Facebook lesson. So good. Why has that happened? I'll tell you what I didn't do, actually. The mistake I made, and I got it right on Facebook yesterday. I should have showed you that if you just put string on top of ice cubes and then take them off again, then the string doesn't stick. That is something that I forgot to do. I should have said, like, just try putting it on, taking it off. It is, you'll just have to believe me that it's the salt that makes it work. Should we see if it works for sugar? Wow, that is awesome. That's so good. That's literally the best that I've ever done this activity. Let's see if it works for sugar. Oh, so close. So close. Never mind. What's going on? Why does that happen? So there's some very, very annoying, not incorrect, but just very vague explanations for this activity on the internet, which I found very frustrating. And I had to spend ages looking up what actually was happening, because it's kind of physics and it's kind of chemistry. Not really my area. Why is the ice frozen? Well, it's because, the ice is warming up, isn't it? So if we were going to look at like what the particles were doing, they would be bonded together because it's ice. The water has been put in the freezer, so it's been kept at below its, what point? You're thinking freezing point because I just said freezer, but it's being kept below its melting point, so it's a solid. Now we've taken the ice cubes out of the freezer. The particles of ice are starting to vibrate more and more and more and more and more, but they're still bonded together, right? So they are getting hotter. If we had a thermometer in there, we'd be able to see they're getting hotter and hotter, but they're still bonded together. It's still a solid. What the salt does is, if you imagine, this is a very bad model of water particles, isn't it? I was going to say that this is liquid water. That's a rubbish diagram of liquid water. Let's make some of them touch each other. It's supposed to be like a ball pool, isn't it? Say that's water. The particles are free to move around, but they are bonded together. They're kind of sliding over each other. When you add salt to the water, what happens is the salt particles get in between the water particles and they basically prevent them from forming bonds, okay? The salt particles get in the way. Don't write that in your exam. But the salt particles prevent the water particles from bonding together. What does that do to the freezing point and the melting point? Sorry, suddenly become very snotty. Well, if you imagine that if these water particles were just on their own, then when they got to 0 degrees, they would be able to bond together and start forming a solid. Because the salt particles are in the way, you have to get it even colder before it becomes a solid. So the melting point and the freezing point of water has been lowered. Yeah, you've got to cool the frozen. This is where my brain starts to go, like move quite slowly, and I start staring into the mid-distance. You've got to cool the liquid water down more. You've got to make it be a lower temperature before it freezes, which is why people put salt on roads, right? Because if it's 0 degrees outside, you're going to get ice forming, which is very dangerous on the roads. But if you can put some salt on the roads, even if it's 0 degrees outside, those water particles can't form a solid. It's going to have to get even colder before it freezes. The reason why this activity always slightly frustrates me is because they always explain that really well everywhere on the internet. Like, oh, you put the string on the ice, you sprinkle the salt on, and that makes the ice melt, so it turns into water. And then it just says, and then the water refreezes around the string. And I was always like, what do you mean it refreezes? How is that a thing? That's not right, is it? That's not what happens. If you put an ice cube out on the side, it doesn't melt and then refreeze because it's not below its melting point anymore. It just melts. It gets warmer and warmer and warmer. That's how science works. What do you mean it refreezes? And then I had to read the answer. I couldn't work it out myself. So I don't know why I'm sitting here in silence expecting you to work it out yourself. It has to do with the salt particles, the concentration of salt particles. Alice did get it on Facebook yesterday. What happens is when you first sprinkle the salt on, you've put loads and loads of salt particles in they're all very concentrated, right? Loads of salt particles all in one spot. So this really reduces the melting point of the water, makes it really low, because there's loads and loads of salt particles really getting in the way. So this ice quickly starts to melt, those water particles can't form a solid anymore. But then of course what happens is, because salt dissolves in water, eventually the salt particles start spreading out and kind of going over the ice. So you've got a much lower concentration of salt particles in that one place. So the freezing point, melting point goes up again, and that water can form a solid because there's fewer salt particles in the way. Is that all right? They're not going to ask you about salt particles like that in your IGCSE physics exam, but I think if you can understand that, it's just a fun activity to do, isn't it, while we talk about melting and boiling points. Shall I show you my little quiz to check how much you've understood? Okay, good. Here we go. So I'm going to show you the graph again that I've showed you before. I'm going to give you a description of what is happening, and I just want you to tell me where on the graph I'm talking about. Okay, here we go. So read the description, then say where on the graph it is happening. Particles are not bonded together at all and are moving faster and faster. Where on this graph is that happening? Particles are not bonded together at all and are moving faster and faster. What do you think? Which bit of the graph is that happening on? Okay, they're not bonded together at all. So we're talking about a gas, aren't we? And they're moving faster and faster, so they are heating up. So that would be anywhere along this red bit of the line is where the particles aren't bonded together at all, and they're moving faster and faster. Next one, particles are vibrating next to each other but not moving around. Particles are vibrating next to each other but not moving around. The vibrations are getting faster. I was quite surprised by how people did not do terribly well with this on Facebook yesterday, so it'll be very interesting to see how you get on. Particles are vibrating next to each other but not moving around. So we're not talking about a liquid, are we? And we're definitely not talking about a gas. But the vibrations are getting faster, so the thing is heating up. So anywhere on that blue line would be fine. So that's when it's a solid. It starts off at 0 times gone by, it's ice. And then all along this line, it's still ice, it's still a solid, still the particles are just vibrating next to each other on the spot, but they're vibrating more and more and more and more and more and more because it's heating up. Particles that were vibrating around a fixed point next to each other are starting to break free and slide across each other. What do you reckon? Particles that were vibrating around a fixed point next to each other are starting to break free and slide across each other. Where is that on this graph? So they were vibrating around a fixed point next to each other. That's what a solid is, isn't it? But now they're not that anymore. They're starting to break free and slide across each other. So that's basically what the melting point is, isn't it? It's when they're just starting to display liquid-like behaviour instead of solid-like behaviour. So that's here, this is your melting point where the solid is starting to melt into the liquid. Particles are starting to bond to each other. Huh? Oh, actually, I think I've made a mistake here, haven't I? Particles are starting to bond to each other. You would sort of have to read the graph backwards, now I think of it, for this to be true. If you're reading the graph backwards, I mean, to be fair, I haven't put arrows on to show which direction if time's going that way, if this is 0 and that's more time, where are particles starting to bond to each other? Sorry, that's a bit tricky. Well, particles in a gas are not bonded together. Particles in a liquid are bonded together. So it must be somewhere along this line, right? If they're just starting to bond to each other, I would say that it's there. They're starting to condense. And this one, particles are bonded but free to move around each other. They are moving faster and faster. Particles are bonded, but they're free to move around each other. They are moving faster and faster. Bit weird, isn't it? So it's not the same bonds in a way. The bonds are being formed and breaking and formed and breaking. They're moving faster and faster and faster. So this is a liquid, isn't it? They're not vibrating next to each other. They're not completely free. They're moving around each other, but they're moving faster and faster. So they are heating up. Yes, so anywhere along that green line would be fine. Phew! Right, you lot. Well done. That is the end of my lesson about changes of state. Felt like quite a sort of nice, neat little lesson today. So I've got 2 weeks off now for the Easter holidays. After the Easter holidays, we are going to be sticking with solids, liquids and gases because, like I say, we need to talk about things like evaporation. We need to talk about the Kelvin scale. We're going to do a little bit more about electricity and how electricity is generated, like your wind and your coal and your gas and all that stuff. Yeah, and then we're sort of skidding towards the end, aren't we? We've got astronomy in our sights and radioactivity. And I think those are the only 2 left before we've completely finished an entire IGCSE physics module, if you've been with me from the beginning of this series, which is amazing. If you haven't, then don't worry about it at all. You can very happily drop into any of those modules without having to have seen the previous modules. Okay, I'm going to have just a cheeky little peep on my Facebook page to see if anybody has left me any comments. I only threw it up like right at the last second, but we'll see. Maybe, well, I was going to start guessing some names, but I won't because it might be awkward if they're not here. Oh yeah, comments! Hello. It's Oh, hello, Edmund. He thinks not everything has a freezing point. Nice one. Let's have a look. As helium does not freeze solid. Are you kidding me, Edmund? I literally did not know that. I am literally looking it up right now. Does helium freeze? Surely if it gets cold enough it freezes. I know that helium... Ah, interesting. Okay. Right. So helium is quite special. You probably know helium from helium balloons. The thing that I knew about helium, which is a really cool fact, although very not useful for humans, is that helium is the only element, it's like the only atom that it can leave Earth and just escape into space. Like the atmosphere is made up of like oxygen, nitrogen, luckily for us, which hangs around. But helium is sort of it's not dense. It just escapes from Earth and just disappears. So yeah, helium doesn't freeze at like atmospheric pressure. So you'd have to put it under a lot of pressure before it froze. That is very interesting. I did not know that. Hello, Laurie. Hello, Bastian. Hello, Kai. And Laurie says it goes flat when it's melting and boiling. The energy is breaking the bonds of the particles. Laurie, that's annoying. I was hoping that I could be like, oh, Laurie, be careful. Be more precise with your language because... Nah, Laurie's got it right, haven't they? It goes, the line of the graph goes flat when it's melting and boiling. The energy is breaking the bonds of the particles. Yeah, breaking the bonds between the particles. Yeah, that's right. Never mind. Good chat. Well done, Kai. Well done, Bastian. Hello. I guess I'll do a quick refresh. Not that I think there's going to be any more comments, but someone, I can't remember whether it was Kai or Laurie, someone last week was the one who reminded me that I had not shown you the answers to the question sheet, which was very annoying. Oh, there is another comment here. Let's see what I've forgotten to do. There's Edmund, Bastian. Oh, Freya! Hello, Freya. Ah, thank you for making it worth me refreshing. Nice to see your comment. Hello. Oh, what are the next topics for next term? Oh yeah, so astronomy and radioactivity are, well, after the Easter holidays, we're going to carry on with this topic, and then we will do radioactivity and then astronomy. I can't remember which way around I wanted to do those. With the all ages lesson, if you're asking me about what's replacing the Vikings, I've actually got no idea. I haven't got a blooming clue. I'll have to poll your adults and we can find out. I haven't said about how you to support me, but it is like the last lesson before the Easter holidays, so it sort of feels like if you're watching, you probably already know how to support me. I've got this page on this website called Coffee. You go to Coffee, you send me £5 or £6 a month, and that entirely funds these lessons. This is my full-time job. I don't teach in a school, I don't do one-to-one, I don't do any kind of tutoring because I haven't got the time. You are my students. If you're watching this, then yeah, you are who I teach now. How weird is that? So cool. So yeah, thank you for supporting me. I'm not going to bang on about it. I'm not going to tell you about all the cool things that you get because I just feel like you know already. I'm going to go and have some honey and lemon. But thank you so much for watching, you lot. If some of you will have already seen all my lessons, hey, for this week. So if you have, then have a lovely Easter holiday from me, at least. I don't know what else you're doing. And I will see you in 2 weeks' time. I've just done another cheeky refresh, but I think we've got everybody. Yeah, we have. Yeah, that's Kai's comment. Okay, good. All right, you lot, thanks so much for coming. See you all very soon.